All right, so we're going to find the local mins and maxes of the following function. Okay, and we're going to do this using the first derivative test. So let me just kind of remind you what we were doing before is we were finding absolutes, maximums, and we do that with critical numbers and testing the critical numbers and testing the endpoints. But now this is your local max. And so we're going to figure out how to find a local max. Okay, so that's the difference between this technique and our previous technique. But they both rely on critical numbers, right? Because the critical numbers, remember, is when the derivative is 0 or undefined. So that's the place we're going to start off. So we're going to run the first derivative test because the first derivative test shows us the local mins and max. Derivative test. And we start that test by finding the critical numbers. Okay? So there you go. And then we figure out the intervals of, that are positive, the intervals that are negative. So the derivative of our little function right here is 4x cubed minus 4x and then plus 0. All right, so we want to know when this is 0. It's defined everywhere, so this part isn't really relative to us. So we're just gonna focus on the zeros. So we have a polynomial equation. So our strategy is to make one side 0. We can factor this. So let's take out the greatest common factor. And then I'm going to keep going. I'm going to factor x squared minus 1 because it's a difference of 2 squares. All right, something like that. Okay, so we can set each factor equal to 0, and then we can see that the critical numbers are c equals, let's see, there's a 0, -1, and 1. Okay, so let's stay organized. I'm going to bring in our little number line that we do, and by organized I mean this. I think we should write down what derivative we're dealing with, because at the end of the section we're going to be dealing with f, we're going to be dealing with the first derivative and the second derivative, and it's really important to stay organized or else we'll get lost in the process. Okay, so here's where our derivative is 0, -1, 0, and 1. So we're going to determine if our function is positive or negative. And we can do it a couple different ways, just like before. If you remember from pre-calculus class, an odd number function has, this end behavior. That's positive. And then all of our zeros are just degree 1. And so our function is going to behave like this. So, perhaps you can see what that's going to look like. So negative right here, and then positive, negative, positive. But if you're not as confident with your pre-calc graphing skills, we can always plug in test points, right? So for instance, here we can plug in like a -2, and then we can look and see how the factors are going to behave. So for instance, this factor with -2 will be negative, this one will be negative, and this one will be negative when we plug in -2. And 3 negatives make a negative. All right, and then little test point, we can try -1/2. First factor will be negative. Second factor will be positive. Third factor will be negative. All right, so now 2 negatives only will be positive. And we continue. We have a 1/2. First factor, positive. Second factor, positive. Third factor, will be negative. So 1 negative means the function's negative. All right, almost done. Last test point could be a 2, and our factors are going to be positive, positive, positive. So no negative numbers, so we're definitely positive. Okay, so we are doing this because we're doing the first derivative test, and this is going to tell us the local mins and max. So either we can go just from the, based off that process right here, or I like to also start from scratch. So for instance, remember this is also telling us when f is increasing or decreasing. So now we're dealing with f down here. So if f is decreasing till x equals -1, and then at -1 we're going to the positive direction, this looks like a local min. All right, and then at 0, right before 0, our function is increasing. We hit the 0, and then the function is decreasing. So at 0, that looks like a max. Same thing with at 1. Right before, since the derivative is negative, our function f is decreasing. We hit the 1, and then derivative is positive. So our function starts increasing. So this is not a max, what I just wrote, that's wrong. This is also a local min. Okay, so there you go. That's the first derivative test. So we can say that x equals, or let me rephrase that. I'm going to say there's local minimums at x equals -1 and 1, and then there's local maxes at x equals 0, okay? And then you normally have to find the value on the function. So if you plug in f of -1, which actually would equal f of 1 since the function's even. Remember, a function's even if all of the exponents are even, and constants, that's like x to the 0. All right, so if all the exponents are even, that means we're an even function. All right, and remember, even functions have this quality. All right, and then you can also plug it into f of 1. Remember, when you're plugging in your min and max values, go back to the original function. That's why this is kind of confusing, because you have to know when do we go to the derivative, when do we go to the function. All right, but moral of the story, you're going to get like 1 minus 2 plus 3. And then f of 0, plug in the 0, and you're going to get a 3. So the local min value is 2, and then the local maximum value is 3. Okay. So there you go. All right, so we know how to find local mins and local maxes. Now we're going to be talking about something called concavity. And there's two types of concavity. There's something called concave upward, and then there's something called concave downward.